are going to write some quadratic equations. So we're going to write an equation in vertex form for the quadratic function that we have the graph of right here. So vertex form in general looks like this. We have our vertex to -9. So we can put those in for h and k because that indicates our vertex in vertex form. If you think about it, looking at the equation that we just wrote there, that one is translated right to and down 9, which is what we need to get our vertex in the right spot. We also need to figure out a. So we have another point it passes through that we can use for an x and y value. If we plug those in, then we'll be able to solve our equation for a to see if this has any vertical stretch or shrink on it. So plugging in 0 and -1 for x and y, let's solve for a. So following some order operations, 0 minus 2 is -2. If you square it, you're going to get 4. And don't forget that's 4 times a. Add 9 to both sides, it's going to give you 8. And then divide by 4, you're going to end up with a equals 2. Putting everything together into our completed vertex form equation, it's going to look like y equals 2 times x minus 2 squared minus 9. So that's our equation of that quadratic function. Okay, so we've got a basketball being shot at a hoop and some information about it. So first off, I like to draw kind of a picture of my situation. I am going to draw my lovely basketball player, so don't judge my stick figure art here. He is shooting a ball up at a hoop. And over time, the height of the ball is changing. So I'm going to let my input value stand for my time. So after 2 seconds, it's 14 feet in the air. That's its maximum. So that's supposed to be my vertex of my parabola. And then that's supposed to be a basketball hoop. And the hoop is 10 feet above the ground, and the ball is passing through it at 3.5 seconds after it's shot. We also have another potential point. So before the ball is shot, it's maybe 6 feet in the air because my player's 6 feet tall, but that one is not necessarily where my ball is at, because just because the guy's 6 feet tall doesn't mean the ball is at that exact location. So when I write my equation of this quadratic, it would be better to use my other 2 points in my model. So starting with my vertex, I know my vertex is at 214, so let's plug those in for h and k, or think about translations, right to up 14. And then to solve for a, to see what kind of coefficient we need in front here, we'll plug in 10 and 3.5 for x and y. And then following order of operations, work inside your parentheses first, and you'll get 1.5. I'm actually going to change that to 3 over 2 because that's easier for me to square. If you square 3 halves, you'll have 9 over 4a plus 14 equals 10. So subtract 14 from both sides is going to give you -4 equals 9/4 a. If I multiply both sides by 4, I could do this in one step and multiply by 4 over 9, but I'm doing it in 2. Multiply both sides by 4, you'll get -16 equals 9a. And then a is going to be -16 over 9. So putting everything back together, my equation that models the path of this ball is -16 ninths times the quantity x minus 2 squared plus 14, which makes sense because it's reflected, it's opening downwards for my path of my ball. So that's a good way to check yourself.